Hey everybody, Mr. Smith here, back for another video lesson, and this time we're continuing to learn about the method of substitution for solving linear systems. But today we're going to use it to solve linear systems that aren't necessarily in slope-intercept or y equals mx plus b form. So let's begin. So it's a bit of a warm-up or motivation problem. Check out the following linear system. So one of the lines is in y equals mx plus b form, so it should be pretty easy to graph that one. The second one is not in y equals mx plus b form. However, it's pretty easy to put in that form. So let's solve this linear system by graphing. So, as usual, it is my hope that you would pause the video and give it a try, and then unpause when you're ready to check your answer. So for our first line, the y-intercept is at -8, and the slope is 1. So I'm doing a drawing of that line, show all my points. And I could graph this one, so I could simply move the 2x term to the right, so like subtracting 2x from both sides. So y equals -2x plus 7. So now that it's in slope-intercept form, I can draw it. The y-intercept is 7, and the slope is -2. So down 2 over 1, down 2 over 1, down 2 over 1. And boom, there we are. There's our point of intersection. It looks like the point 5, -3. So again, if your system is not, if the lines are not in y equals mx plus b form, you could still solve by graphing by rearranging them. Now, this rearranging, so as we've already talked about, solving by graphing is impractical a lot of times, and also rearranging can be impractical too. You may not want to rearrange your equation. You may not enjoy doing that. So today we're going to learn a way to solve systems like this algebraically, where they're both not in y equals mx plus b form. All right, so let's look at the same linear system, and let's, as a bit of a warm-up, let's use, I say yesterday's here, but or whenever you did the last lesson, I guess I should say, and this it should say rearranged version of equation 2. So we have, I'm going to rewrite our equations out. We have y equals x minus 8. In our rearranged version of our second equation was y equals -2x plus 7. And our strategy was, hopefully you're very practiced up now, set equation 1 equal to equation 2. X minus 8 equals -2x plus 7. Let's add 2x to both sides. 3x minus 8 equals 7. Let's add 8 to both sides. 3x equals 15. Oh no, 3 times 5 is 15. So x equals 5. Just as we expected it to. And equation 1 looks easy to work with, so let's sub that into equation 1. Y is equal to 5 minus 8, 5 minus 8, -3. So we get the same answer. We get the point of intersection of 5 minus 3. So 2 ways to solve a linear system. You can graph it, and in this case, we had to rearrange one of the equations, but you could still do it. And if the linear system is not quite both in y equals mx plus b form, and you'd like to use substitution, you can just rearrange and make them both in y equals mx plus b form, and then solve just like we did last lesson. But is there a more efficient way where we don't have to do any rearranging? And there is. So we're going to solve this equation one more way. I'm going to show you guys the strategy. So, and it's just a more general substitution method. Either one of those methods actually worked pretty fine. None of them took a long time, but we want a more general method for just to cover all of our bases. And the key idea we're going to use is this. So to use the method of substitution in a more general way, we're going to isolate a variable in one of the equations and then substitute it in the other. Now, when I say a variable, right now we've been getting the equations in the form y equals, but that doesn't have to be true. We could actually isolate an x instead, and I'm going to show you guys that in a few examples here. So let's go back to this, our original guy, and do it one more way. So I got to flip back and see what the equations are again. I'm only 38, but my short-term memory. X minus 8, x minus 8, and then that was our equation 1. And the original equation 2 was 2x plus y equals 7. All right, so follow along here, guys. So here's the idea. If you look at equation 1 is saying that y, whatever y is equal to x minus 8. Well, if y is equal to x minus 8, why don't I just substitute that into my second equation? Replace y with x minus 8. And I'm going to, oops, I forgot the 1 there. I'm going to write that as, I'm going to sub equation 1 into equation 2. What does that look like? So equation 2 is 2x plus y equals 7. But I'm going to take what y is equal to, x minus 8, and replace y with x minus 8. So just compare. Just take a moment for this to digest. I took equation 2, 2x plus y equals 7, but y is equal to x minus 8. So I replaced y with what it's equal to, x minus 8. And what you'll notice is this is an equation that only has x in it, and we can solve for x. Now, there's nothing, I like when I'm substituting in, I like to write in brackets around what I'm substituting in. In this case, nothing is being multiplied by that bracket. It's just like a 1. So I can just drop the brackets basically. So 2x plus x minus 8 equals 7. And now this is actually a fairly simple equation to solve. 2x plus x is 3x. Remember, if you can collect like terms on the same side, do so. Add 8 to each side. We get 3x equals 15. So it should look familiar. We get x equals 5, just like we did before. And at this point, it's the same strategy. We're just using substitution to find our value for y. We're going to sub x equals 5 into, now you always have a choice, but in this particular way of viewing this problem, only one of our original equations is kind of practical to sub x equals 5 into. And in this equation 1, because equation 1 is already set up for us to find y. Y equals 5, subtract 8, y equals negative 3. And again, we get the same answer. But just a more general way of doing things. One variable is isolated. You sub what that variable is equal to into the second equation. So let's try some more. Ultimately, we just have to get experience to build up our comfort level. So let's look at a new linear system. So we are not going to graph this one. And I would argue, like looking at that second one, I don't think I would want to graph that one. Let's use our algebraic method. So notice here, again, one of the variables is already isolated for you. Y equals, it's by itself. So let's sub, because equation 1 is isolated, let's sub equation 1 in equation 2 again. And this will give us 2x minus 3y, but y is equal to, remember we're subbing in equation 1, y is equal to negative 3x plus 4, and then equals 32. And we have no more y. This is an equation that's just in terms of x, and we can solve for it. So let's continue. So using our distributive law, we have minus 3 times minus 3x. So careful there, that's 9x. Minus 3 times 4 is minus 12, equals 32. We can add these guys, 2x and 9x, add to 11x. And then add 12 to both sides. We get 11x equals 44. That's good because 44 divided by 11 is exactly 4. So we have created an equation with only one variable, x here, that we could solve for by substituting one equation into the other. And the last step is always the same. We're going to find the other variable, in this case y, by subbing x equals 4 into an equation 1 is the guy that's isolated. So minus 3 times 4 plus 4. It's minus 12 plus 4 minus 8. Do that. And we have found our point of intersection. The point of intersection is 4 minus 8. And we've got it, guys. So a second example in the books. Now, in these cases, both of these were kind of set up well for you. One of the equations was already isolated. Let's do another example where that's not the case. So check this one out. 2x plus 3y equals 9. And x minus 2y equals 1. So neither of those are in y equals mx plus b form. And if you check out, think about what would happen if you wanted to isolate for y. If I wanted to rearrange equation 1 for y, eventually I would have to divide by 3, and I would get some fractions. And the same thing with equation 2. Eventually, if I wanted to isolate y, I could, but I'd have to divide by 2, and I'd have to introduce some fractions. And I don't know about you, I like to avoid fractions when I can. In this case, there's one good choice for a variable to isolate, and it's the x in equation 2. It's the only variable in either equation that's by itself with no number in front of it or anything. So let's rearrange equation 2, just writing it in a different form. We can bring minus 2y to the right, and we get x equals, it becomes positive 2y. And then we have that plus 1 over there. And that's just an alternate form of equation 2. So it's our very first example where we're rearranging the equation. Maybe it isn't exactly intuitive to write the x out front, but here we got the x by itself. So now what happens? Let's check this out, guys. This time we have equation 2 isolated. We're going to sub equation 2 into equation 1. Check this out. So 2x, and x is equal to 2y plus 1. So we're going to put in 2y plus 1. We still have the plus 3y equals 9. And now in this particular problem, we're finding the y first instead of the x, which is cool. This one's not so bad. Little distributive law. 2 times 2y is 4y plus 2 plus 3y equals 9. Again, always look for collecting those like terms on the same side. 4y and 3y is 7y plus 2 equals 9. I'm running out of space, so I might just visualize it this way. If you bring over the 2 and subtract it, you're going to get 7. So 7y equals 7. And hopefully we're all okay with the fact that 7 times 1 is equal to 7. We found the y value. This is the first one, I think, where we found the y value first. That's no big deal. We found the y value. Now let's find the x value. Let's sub y equals 1 into, well, which equation will work? Either one will work. But you know what? Equation 2 is already rearranged for us. We know that from equation 2, x equals 2 times y, or 1, plus 1. 2 plus 1, we get x is equal to 3. And so the point of intersection is 3, 1. And we've got it. So our first example of isolating for x instead of y. And why did we isolate the x? Because it was by itself, it was easy to rearrange, and we're just left with x equals, which meant we could replace x in the first equation with what it's equal to. All right, so I believe, yeah, this is the last one I have for you guys in the lesson anyway, and then you guys can get practicing. Because ultimately, and I'll just go off on a short tangent here, it's all well and good to, go through an example with me, and you might even get it right away. So yeah, that makes sense. But ultimately, you want to be able to solve linear systems using, and not have to like agonize and spend, a lot of time and a lot of brain power. You just want to kind of know the steps and implement the steps and just systematically work through it, without having to dig deep, right? And the way you get that is by practicing. So, when we're done the video lesson and you've been provided some practice, it's best just to practice as much as you can. That's how you get good. It's just like a sport. All right, so if you want to pause the video, which variable are you going to isolate from which equation? And then can you implement our substitution strategy to finish it off? If you want to unpause when you're ready, here we go. If you said isolate for the y in equation 2, good for you, because it's all by itself. There's no number in front of it. It's going to make it easy to rearrange. We get y is equal to, bring over the 4x, negative 4x plus 5. So that's just a rearranged equation 2. And now we're ready to go. We're going to sub our rearranged equation 2 into equation 1. So we have 2x plus 5, and y is equal to negative 4x plus 5 equals 7. 2x minus 20x, I'm using the distributive law, plus 25 equals 7. So we might get a fraction here, unless I'm doing my mental math wrong. So 2x minus 20x is negative 18x. Plus 25. Oh, no, I think we're good. Subtract 25 from each side. Negative 18x. 7 take away 25 is actually exactly negative 18. And so we get x equals to positive 1 when you divide negative 18 by negative 18. That's great. So we know x, let's find y. Which equation will we use? Equation 2, it's already rearranged for us. So sub x equals 1 into equation 2. Y is equal to negative 4 times 1 plus 5. Negative 4 plus 5 is 1. So y is also equal to 1. So after all that, the point of intersection is actually just 1, 1. And yeah, everything fits. 2 plus 5 is 7. 4 plus 1 is 5. So great. Another example in the books, but you definitely need this. You need to practice. You need to practice identifying when this method is a good one to use. And it's a good one to use when you can see a variable all by itself. It's easy to isolate. Then you can sub it in, and it's just a bit of solving equations. And none of the equations you get with this method are overly complicated. You're going to have to use a distributive law most of the time, collect some like terms, two-step solving. So there are several steps, but I would argue each step is manageable. You guys can do it. So up next, this method was great. As long as you can easily isolate a variable, like in the examples we did. But what if your system looked like this? So 7x minus 3y equals 7. None of those are easy to isolate. Same with this second equation. It's not easy to get x or y by itself. If we wanted to isolate a variable, we could do it, but we'd have to introduce fractions. And I would not like to do that. And I'm sure you would not like that either. So what we want to do is we want to find a way that can help in situations like these. Another method. And so this will be the final method we'll learn. I'm looking forward to it. But until then, hope you guys are staying well. Have a great day, and we'll see